Okay, welcome back to another lecture. So in the previous lecture, you guys learned, everyone learned about bracket notation or the Dirac notation about cats, bras, unitary operations, measurements, projectors. There's a lot. I mean, I learned this in multiple weeks in college, and you're learning it essentially in a day. We don't know if you understood it or you don't understand anything at all, or only some of you understood it. So just to test that we're on the same page, I would like to ask some questions that might help us recap a little bit before I move on to an algorithm that uses this grammar. If you have a bad grammar, you can't write an essay, right? So at least let's make sure that we're on the same page. So I would really appreciate it if someone could make an attempt to answer what this quantity would be. So this is a ket vector 1 that is being dotted with a bra 0. What do you think the answer to this is? 0. Okay. Why is it a number, a scalar? Okay, 2 people have answered it. Thanks a lot to Anthony and Jaslyn, if I'm not butchering your name. Why is it a scalar and not a vector? Because I am operating on 2 vectors right now. Okay, yeah. So I'll use this notation. Okay. So just for the purpose of recap, right? So Jonas taught you guys that, ket vectors are essentially represented by the vectors that we learn in school, right? High school, college. So this notation means is represented by. So these are the same things. So this ket vector 0 is represented by this column vector 1, 0. And the bra is just a transpose of this. And so you just need to transpose this. And transposing this means you have this. So if you write down the dimension of this vector, right, it's a 2 by 1, 2 by 1 vector. And this is what? What is the dimension of this vector? Anyone? 1 by 2, thanks a lot. 1 by 2, right? So we learned this, that if we operate a 1 by 2 matrix, let's say M on a 2 by 1 matrix, then we would end up with something, let's say Q, that has a dimension 1 by 1, right? Because this is common. So it's a number. So the reason why physicists or people in quantum computing like to use Dirac notation or the bracket notation, not the Amazon bracket, is very easy to read things off. So whenever you see any quantity that starts with this arrow and ends with this arrow, it's always a number. It's always a scalar. Unless the person is defining a certain axiom or defining it in a certain specific way, which is rare, by the way. This is always a number. So if there was, let's say, some operator x, right? For example, the x gate, then before I even compute this quantity, I would know that this is going to be a number because it looks like it's ending up with an arrow. Now, if you look deeper at this, you'll see that, well, to calculate this, I first calculate x on 1, right? Now, this is just your bit flip operator acting on 1. What is x on 1? So what does the bit flip operator flip 1 to? It flips it to 0, right? So, and if you take the inner product between 0 with itself, it's just going to be 1. Okay, so if you ever get confused with Dirac notation, sometimes it might help to go to the way we learn linear algebra is by writing down the coordinates and maybe coming back. And doing this back and forth might you might eventually get with the notation. Okay, this is great. Okay, so because I'll be using this notation. So I'll be using something like psi operator A, something like this. And before you know, like before you get overwhelmed by this notation, you know that it's going to be some number, right? And so there's another thing I need to mention. So something called expectation value. Okay. This is also going to be useful. So expectation value is, Jonas said that it's defined as, so if you have, so let me first introduce this. Okay. So suppose you have a state 0 and you want to compute expectation value of 0 with respect to its eigenstate. Sorry, the eigenstate of x is not 0. Let's use z. Okay. So Jonas said that the definition of g is just this guy. Now if you look at this operator z, right? Obviously you can write a matrix form of this. If you simplify this, you'll see that it's just this matrix. But actually, the reason for actually having this operator form is you can just look at the operator and you'll know what it does. So what does the z operator do? Well, the first part of it, right, this first part, it tells you that it takes us input at 0 and it throws back 0. So for example, if you apply 0 on z, what you get is 0, 0 acting on 0, right? Minus 1, 1 acting on 0, okay? And so what is this quantity? So if you just look at this, you just take inner product of 0 with 0, which is just 1. So you're left with this ket 0, right? Minus, what is this quantity? Inner product of 1 with 0. Anyone? I can see that someone wrote a 0, but this was a while ago, but it's the same answer, right? So if you take inner product of 1 with 0, it's 0, right? So this term just vanishes. So you have nothing here, and so you're just left with 0, right? And we could mathematically verify it, but we can actually just read it off. We can just read it off by saying that it takes input vector 0 and it leaves it unchanged, but it takes input vector 1 and gives out -1. So basically it's saying that z acting on 0 is 0 and z acting on 1 is -1, right? So basically it just flips the sign of 1, but leaves 0 unchanged, right? And that's the definition of g. And we can just read it off by just looking at the notation, okay? It's a trivial fact, but this translates to all the operators written in a Dirac notation. Okay. All right. So that's one thing I wanted to ask. The other question I also wanted to ask to make sure that you understand superposition is, okay, so Jonas told you that, and you guys learned that 0, 0, if you apply Hadamard and C naught, you get to a Bell state, right? So Bell state acting on 0, 0, and it looks something like this. 0, 0 plus 1, 1. But this is actually not the only Bell states. There are also other Bell states. So if you start with state 1, 0, for example, and apply Hadamard and C naught, what do you get? So to answer this question, first let's apply Hadamard, right? So if you apply Hadamard, okay, so let's go through this step by step, okay? So if you apply Hadamard on 1, 0, and by the way, this could be confusing to some of you. It used to be for me, but if you have 2 bit strings written in ket, it just means tensor product, right? It just means this. And this is defined like this. So 3 lines means this is defined like this, or you can also use something like this. Don't get confused. So this and this is the same thing. Okay. So 1, 0. When I say Hadamard, so basically you need to understand that the dimension is not correct, right? Because Hadamard is a single qubit gate, and 1, 0, I have a 2 qubit state. So the implicit assumption that I'm making here is that Hadamard is acting on the first qubit like this, and then I leave the second qubit unchanged. So Hadamard is actually not acting on the second qubit. Uh, Usually people will specify it. If they don't, then you can assume that the gate that is specified acts on the first qubit. Okay. So Hadamard acting on 1, what does it become? Can someone tell me what happens when I apply Hadamard on the state 1? If we don't go through this, I can't go through the Deutsch-Jozsa algorithm lecture. Anyone? Any guesses?
It goes into superposition.
It goes into equal superposition.
One
That's
plus zero, get 1 plus get 0 over root 2.
okay. So is it something like this? Is it?
Yes.
Okay. Okay. Thanks a lot for your response. So the equal superposition part is absolutely spot on. So but you also probably learned that Hadamard acting on the 0 state is this state, right? Hadamard acting on the 1 state. So is it true that Hadamard acting on both 0 and 1 state? So this is defined as, again, so this superposition state is defined as the plus state, okay? So is it true that if you apply Hadamard on 0 and 1, it takes you to the same state? So in the block sphere representation, okay.
Oh, 0 minus 1, I think.
0 minus 1. Okay, excellent. Yeah, that is correct. And this is also known as the minus state. Okay, so in the block sphere representation, right? Where so this is your z-axis, x-axis, your y-axis. Usually in the block sphere, 0 is defined as the upward direction, 1 is defined as the downward direction, and your plus state, right? Your plus state actually lies on this x-axis, along this x-axis, and minus state actually lies on the opposite side. So if you apply the Hadamard gate, what it does is it takes you from 0 state to this plus state, okay? And if you apply if you apply Hadamard on this 1 state, it takes you to this minus state. So what it is doing is it's basically doing rotation, right? Where it's taking your state from 0, and it's taking you to this x state. Sorry, this plus state, right? And the rotation is on the same direction because the definition of Hadamard is the same, right? Regardless of what state you acted on, it has the same property with different phrases. Yes, Nima, thanks. Different phases. So this is going to be a plus state, this is going to be minus state. So the definition of Hadamard, right, is essentially this. Okay, so actually, let me ask you. So if the definition of Z state is this in the Dirac notation, what is the definition of Hadamard? So we have the complete definition here, right? What does it tell you? It tells you that if you apply it on the 0 state, it takes you to the plus state. If you apply it on the 1 state, it takes you to the minus state, right? So how do I write it in the Dirac notation form? Anybody? Please type. It's probably hard to type, but you can. Please unmute yourself. Anyone? And then try to read it off. Any attempts would be really appreciated. So also one thing, so Hadamard has a matrix representation. Okay, any operator has a matrix any linear operator has a matrix representation, but Hadamard has this matrix representation. Okay, so if you can't see where this came from, right, where this plus state minus state came from, just apply this on your on the state here. Okay, and you'll see where this is coming from. Okay. Uh, so let me start this off, right? So by definition, what it is doing is taking zero state as input, right? And it's throwing off the plus state, correct? So that would be my first term. Now, but in this definition, right, it is very important that the 0 and 1 is orthogonal, which means if you take the inner product, it's 0, right? So you can check that that is the case. So if you take the inner product between the plus state and the minus state, it's 0. What does that mean? That means that these two vectors are orthogonal, right? You can see this in this block sphere representation as well. Although in block sphere, what happens is, there is one caveat here. In block sphere, vectors that are orthogonal lie exactly opposite to each other. So diametrically opposite to each other. Okay. So for example, 0 state is orthogonal to the 1 state, right? So it is on the exact opposite direction. So same with the plus and the minus state. Okay. So make sure to keep this in mind. So far we know that 0 and 1 is orthogonal. We know that plus and minus is orthogonal. And we know that Hadamard is defined. We have a half definition. So is anyone, I would really appreciate if someone could tell me the second term in this direct notation form. Okay. Plus, because the first response was plus 0 plus minus minus 1 could work. Minus 1. Okay, yeah. So I think we have answers coming here. So basically it's saying that it acts on the 1 state and takes you to the minus state, right? And that's what Hadamard is basically doing. Okay. So by definition of this operator, okay, so we're not thinking of it as a matrix, but as an operator, and it looks something like this. But also notice that this also works. Also notice that this also works. So this is important. Okay, so what did I do? What does this mean? So this says that if you apply Hadamard on the plus state, it takes you to 0. And if you apply it on the minus state, it takes you to 1. Now you can verify this. Okay, let's just do it very quickly. So if we apply Hadamard on the plus state, for example, then what do you have? So let's look at the first term. So you have this guy acting on the plus state, right? So this acts on it. You get 0, right? And the other guy, 1 minus this acting on the plus state. So as I said, this is just 0, right? So this whole term is killed. So you're just left with 0. And you can verify the other term as well. So you can also write down Hadamard in this manner, right? So this is not a coincidence. This is true because both of these two operators are self-adjoint or Hermitian. So Jonas mentioned this before in the lecture, but you can verify that if you take a conjugate transpose of these operators, they're just equal to itself. And same with Hadamard. Okay. So you can do this if you look at the matrix, right? If you look at 1, 0, 0, minus 1, what happens if you take conjugate transpose? So conjugate transpose has two things. First, you take the conjugate, and conjugate is complex conjugate, okay? So for example, someone who doesn't know what conjugate is, Z star or needs a recap. So let's say you have a complex number Z defined as A plus IB, then Z star is what? Complex conjugate of this, which is A minus IB. If it's a real number, it's just the same thing. So if you take a star of this, it's itself, right? Because all numbers are real. So the complex conjugate of the real number is real. But if you also transpose it, which means I take the column and write it as row, take the column and write it as row, it's itself, right? And so if you change the order, like in this manner, you'll see that both of these definitions work. Okay, so I would like you to familiarize yourself with these ideas. It's not really ideas, actually. It's just notations and an idea or intuition behind block spheres, because this notation is easily scalable, right? What I mean by that is, okay, if I want to write down an n qubit system, if I work with vectors, what do I need to do? I need to write down 2 to the n coefficients, right? And I will need to write down 2 to the n by 2 to the n matrix, right? It's very complex to write down. But using the Dirac notation, I can just write it down as a summation over some vectors that are tensor producting with each other, something like this. So basically, they have a very easily representable forms. That's why we want to use with Dirac notations. Okay. 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 Great. So, oh, I think with this, we are ready to go to learn about one of the first algorithms, one of the first quantum algorithms, to show that it is significantly better for certain tasks compared to classical algorithms. So, okay, so sorry, there was one thing I also wanted to go through. Yeah, so can we go through this one last time? So what happens when you apply Hadamard and C naught on 1, 0? Okay, so let's apply Hadamard first, okay? So let's do Hadamard first, okay? So this is a 2-qubit state, right? So 1 tensor 0. So I'm applying Hadamard on which state? The first qubit I said, right? So on the first qubit, like this. Okay, I'm putting parentheses here because I'm trying to imply that H is only acting on the first qubit, right? Not on the second qubit, okay? And so if you apply Hadamard on the one state, what do you get? So someone already answered. The answer is 1 over square root of 2, 0 minus 1, right? This is also called the minus state, okay? So it's written like this. So the definition of plus and the minus state is 0 plus minus 1, okay? So this basically means if you take plus, you have plus sign. If you take minus, you have minus sign, okay? Tensor 0. Now, what you can do is you can use linearity, the property of linearity, right? And what do you get? So 0 tensor 0, you can write it as 0, 0. 1 tensor is 0, just 1, 0, right? This is just representation. Okay, now I need to apply C naught on this, okay? So what happens if I apply C naught on 0, 0? Okay, what is the definition of the control NOT gate? Nothing happens. Yes, nothing happens. What is the definition of control NOT gate? Yeah, okay, so the answers are coming. Okay, so basically 0, 0, 0 remains unchanged. 1, 0 becomes 1, 1, very good. So what is happening is the control NOT gate basically looks at the first qubit. So control NOT gate if it's in this representation where you have a qubit here, let's say qubit 0, qubit 1, and this is called the control qubit, and this is called the target qubit. Okay, this is the representation in a quantum circuit. So if the first qubit is controlled, then it flips the qubit 1, depending on whatever it is, to other states. So if it's 0, it becomes 1. If it's 1, it becomes 0, right? Given that this qubit was 1. So if it was originally on the 1 state, then only control gate acts. If it's originally 0, then it does nothing, right? So that's the definition of the control NOT gate, okay? So basically what it is doing, it leaves this unchanged and flips the bit of the second qubit, right? Because, and this is the definition of control NOT gate. So actually, not just Hadamard and Z, right? Control NOT gate also has this Dirac notation. So I'm just gonna give it to you, what it does. So basically let's write it down. I hope this is intuitive. So the definition is, if the first qubit is 0, then do nothing, which means tensor identity on the second qubit. Okay. So if my first qubit has state 0, then I do nothing on the second qubit, right? So I leave the first qubit unchanged, first of all. Okay. So the way to construct this would be, okay, if I'm acting on something, I will write it as a bra like this. And then I'll tell, okay, C naught doesn't do anything on the first qubit, leaves it unchanged. And the second qubit is also unchanged. Okay. Plus, if the second qubit is in the state 1, like this, then I'm going to apply X on the second qubit. Sorry, so if the first qubit is in the state 1, then, okay, C naught doesn't do anything on the qubit that, on the first qubit, right? So something to remember is this qubit is unchanged, by the way, okay? The control qubit, which is called, says control qubit, is unchanged, and this target qubit gets flipped, right? So if it's 0, it becomes 1. If it's 1, it becomes 0. Okay, so this is your Dirac notation definition of a C naught gate. Okay, and X, okay, so I should also define X. So C is defined as this guy, right? So the phase flip operator, also known as phase flip operator. Why is it called phase flip? Because it leaves 0 unchanged, but it gives you the sign -1 to one state. So X, what does X do? Can someone tell me definition of X in Dirac notation? So if it takes 0, what does it do? It gives me back one state. Excellent. Plus, if it takes the one state, what does it do? It gives me the 0 state. Yeah. Okay, great. So yeah, this is how we familiarize ourselves with the Dirac notation. Okay. Now this language, this grammar that you learned, will be transferred to the algorithms portion. But before I do that, one thing to comment on is we started with a 2-qubit state, right? That was something like 1 tensor 0. But I have ended up in this state where I have two terms, which means this is a superposition of this first state and the second state, right? Let me actually not. Oh yeah, so okay. So this state transforms into superposition of two different states, right? So that's the idea of superposition that comes along with quantum computing. But the second idea that should also be mentioned is that these two qubits are actually something called entangled. What does that mean? That means that if you look at the result, right, I can close my eyes and I can, if I only know the state of the first qubit, I know that the second qubit is also in the same state, 0. And if I know the state of the first qubit as 1, then I know that the second qubit is also as 1, and vice versa, right? So the idea of entanglement is that I don't need to know information about the second qubit if I know the information about the first qubit. Okay, so the formal definition is that a qubit is entangled if it simply cannot be separated into tensor product of two different states. So if you try to find a decomposition for this state, which you can, right? So just try this, right? So try this as alpha 0, beta 1, and then let's say alpha 1, beta 1, alpha 2, beta 2, and then try to solve for this. Try to solve for these four coefficients. You'll realize that none exist to give you back these states. So we don't actually care about the phase here, right? It could be plus, it could be minus. It could also be this state, by the way. It doesn't have to be the same thing. It can also be different. So this state is also entangled. Why is this entangled? Why is this state entangled? This is also a Bell state, by the way. So by definition, right, because we can't solve for these coefficients, yeah, exactly. So one is conditioned to other, which means that if I know the state of the first qubit, if I knew that it's 0, then the second qubit is simply the bit flip of the first qubit, which is 1, right? And if I know that the state of the first qubit is 1, then I don't need to know the state of the second qubit. I just know that it's the bit flip of this state, which is 0, right? And the same thing applies in the other way, on the other direction. So if I know the state of the second qubit is 0, I know that the state of the first qubit is just bit flip of that. So 0 bit flip 1, 1 bit flip 0, right? So this is the law of entanglement that we just see here. And Bell state is used for instructional purposes purely because it conveys two ideas in just one state. So it conveys the idea of superposition here between two states, and it conveys the idea of entanglement. Okay. One final thing is, if I measure this state, what outcomes will I get? What are the outcomes I'll get if I measure these two, this state? This is not two states, actually. This is a single state. So the measurement outcomes are, so the first qubit will be 0, 1. Sorry, the first qubit will be measured as 0, and the second qubit will be measured as 1. And this comes with probability 1/2, right? So you learn this in Brazil's lecture, Jonas's lecture, that only the terms in the equation are measurement outcomes, okay? And I also measure 1, 0 with probability 1/2. And this probability is basically given by norm square of the amplitudes, right? So this is superposition because I was able to measure two different states, okay? So superposition, entanglement, and Dirac notation is all you need to know. And unitary operations is all you need to know to learn quantum computing and quantum algorithms. Okay, so with this, any questions? Any questions about this brief recap, summary, whatever it is? No questions at all? Reading materials for bracket notation. Yes, we'll send you links to the so we'll assemble a list of links in like a set of priorities, but if you just click on the first link and read it, that should suffice. Okay, so there are actually tons of materials out there that are public and online on this. And so if you go through this, and you'll need to use it as a reference for tomorrow's lecture, because I'm going to go into quantum Fourier transform, which is going to be a mess, a really messy essay if you can't understand this grammar, as I said. Okay, so we're going to run out of time, so let's go through the Deutsch-Jozsa algorithm. You're welcome, Nima. Okay, so let me stop sharing my screen first, and I'll share my slides. Okay. Okay, share screen. I'm sorry about my flip background. I still haven't figured out how to do it. Hopefully I do it by tomorrow, but no promises on that. But I will promise that we'll have the link prepared for you, okay? Right. So slideshow, they don't start. Okay. Can you see my screen? I can see from my iPad, which means you.
Yes, we're good.
Okay, excellent. All right. So Deutsch's algorithm, I actually fought for keeping this lecture. Before we actually planned to start from quantum Fourier transform. The reason for this is because Deutsch's algorithm was one of the first algorithms to show quantum speed up. We'll talk about what that means. And secondly, it's simple enough that a beginner can understand it, or anyone can appreciate it if you just understand the basic vocabulary, which is the direct notation. Okay. So let's go into the problem formulation. So the description of the problem is as follows. Okay. So the description is, suppose you're given this black box binary function. What does that mean? So an example of a black box function is a bitlib operator. So in classical setting, what does the bitlib operator do? It flips 0 to 1. It flips 1 to 0. But you don't need to know what it how it does it, right? You don't need to know the inside mechanics of it. So you can treat it as a black box function. And it has a quantum, we also have a quantum bitlib operator, right? Which works on qubits. So that's an example of that can be treated as an example of a black box function. So note that by definition, function fx is binary, which means it acts on only zeros and ones, and it outputs zeros and ones. Okay, so that's what it means that x and y is in this set 0, 1, which means x and y can only take the values of zeros and ones, and the function also outputs zeros and ones. Okay, that's the assume that you're given this black box function. Okay, the objective of your objective is to determine whatever this function is. We don't know, it's a black box. Okay, we just know the input types and the output types. The objective of this function, or your objective, is to determine whether this function is constant or balanced, which means if I apply it on my input, 50% of the x values will result in fx equals to 0, which means, okay, so I'll use my iPad to write down a bit more on what this means. But basically, this function, your goal is to determine whether this function is constant or balanced. Okay. The restriction that you're given is you are allowed to query this black box function with whatever input choice you want. Okay. And your goal is to solve this problem using as few queries as possible. All right. So let me go to my iPad and okay, so I'll make a new file. Okay, so it's just Deutsch-Jozsa Algorithm. And I'll share my screen, okay? Okay, let me share my screen on my iPad. Meanwhile, just take a moment to digest these 4 things on this slide. And I'll explain what constant and balanced means, okay? Share screen, share. Okay. So, okay. So what you have is this function, right? That acts on bit strings x and y. Oh, sorry, I am not sharing my iPad screen, am I? I am, okay. So this gives me this thing, okay? So your goal is to determine if fx equals to 0, which means means it's constant. Okay, so your goal is to determine if this function for all x, by the way, for all whatever input strings is 0 for fx equals to 0 for all x. Okay, this just means all, by the way. Or and this means constant, as I said. And then balanced. Balanced means for 50% of the time, for 50% of fx is 0, and the rest of the time fx is 1. Okay. Now let's write this down properly. So you have x, you have fx. Okay, this is written as a quantum circuit, but you can also think of this as a classical Boolean function as well. And we'll want to compare what quantum and how quantum and classical compares to solve this problem. And so you have your output. So you are promised, by the way, so you are promised that this function is either constant or balanced. Okay, so the promise is that this is a Boolean function, and you also promised that fx is either constant or balanced. Okay, so 50% of the for 50% of values that you pass, fx will output is 0, and for 50% of the values, you'll output 1. Okay, solve you okay, so this is your promise. Sorry, this is the description. This is your goal. Okay, so this is your goal. Goal is to determine if this is constant or balanced, but the caveat is obviously with fewest queries that you can. Okay, fewest queries possible. Okay, so first of all, before we even think about how to do this quantumly, let's think about how to solve this problem classically, or how many queries do we need to solve this? So the question I want to ask you is, how many queries do we need to solve this? Okay. Someone says 2. Okay, that's a nice guess. Okay, Nelson says 1, classically 1, okay. Can any of you explain your thought process? So the person who said 2, okay, Nima says many. For the person who said 2, can you please explain your thought process? Try just over 50% of possible inputs, Anthony says. Okay, I think the answer is coming out. But can anyone, I would really appreciate this, can anyone explain the thought process? Why? Might be obvious to some, but might not be to others. Why is it that, if you could unmute and, okay, Emily says 3. Anyone? Especially with the people who have responded on chat. Okay, Emily says try 0, try 1, either 0 or again. If so, you get the full set of options from the output. Okay.
I think because we don't understand the order of inputs, we need to try it many times, and then assess the probabilistic outcome and see if it's a constant function or changing 50% of time.
Yeah. Yeah, that's correct. So you need at least 2 queries is the answer. Okay. So let's say I apply my fx. First time I get 0. And then I apply it again. And I get 0 again. Then I know that this is a constant function. Right? So, however, if I apply fx equals 0, okay, so that's the first outcome I get. So it doesn't matter whatever outcome I get, right? I just need to query this 2 times. So you can compare these two scenarios, okay? Sorry, actually you need to check a third time to see the third time to do a tiebreaker, right? Because it's possible that the third time this can give you 1, right? And the fourth time this can give you 1, right? So so you need to do check this at least 3 times. Okay. So let's say you check 3 times and you're lucky. You know that this is going to be a constant function. Okay. Because half of the time, if it was not, half of the time it will be 0 and half of the time it will be 1. If it is balanced, however, it would be something like this. So let's say it gives you 0, 1, and then 0. Then you would know that this is going to be a balanced function, because a constant function would never give you 1, right? So actually, a simple way to answer this is just do your queries, and if you don't end up with 1, if you end up with 1, then you know that it's a balanced function, and otherwise it's going to be constant. So you need to query this at least. So this is actually quite important. So you need to query this at least 3 times. Okay. Sorry, there are multiple comments I see. From Pascal. Yeah, so it's important to remember that. So we'll see the example of this manifest itself. Okay, which is quantum entanglement and superposition quantum entanglement and superposition are the key concepts necessary for quantum speedup. Thank you. For a balanced function, does it mean that the first result is 0? Is the second result definitely 1? Or is it just statistically 1? Sorry. If the first result is 0, is the second result definitely 1? Oh yeah, so sorry, yeah. So it's you guarantee that it's just statistically 50-50. Yeah, I hope that answers your question.